The Barents Sea in late January makes no distinction between ocean and atmosphere. At 72 degrees north in winter, the surface temperature is -1 to +2 degrees Celsius. The air temperature runs between -22 and -31. And the northeast wind drives a continuous aerosol of spray, ice crystals, and spindrift that coats every external surface within minutes. A ship operating here is not operating on the sea. She is operating inside a system that is simultaneously freezing, pressurizing, and abrading every exposed component from the outside, while her own mechanical systems generate heat and vibration from within. USS Bainbridge makes 19 knots on a southwesterly heading, 280 nautical miles northeast of Tromsø in the Barents Sea. She has been on this patrol line for 9 days as part of a NATO observation tasking, monitoring Northern Fleet submarine activity, following an unusual increase in Severodvinsk-class SSN transits through the Barents egress corridor. The observation tasking has been productive. The ship's acoustic sensors and electronic warfare suite have generated significant intelligence and has been unremarkable in every operational sense. The watch routine has settled into the pattern that long patrols develop. Alert but habituated, focused on the monitoring task, aware of the environment but adapted to it. The ice accretion on the superstructure is chipped every 2 hours. The heating systems are running at maximum output. The crew wears cold weather gear indoors and survival suits outdoors. They have been doing this for 9 days. It is 3:41 a.m. when the pattern ends. The 53 to 65K torpedo was developed by the Soviet Navy as a wake-homing system. It does not need an active sonar ping that would reveal the firing platform. And it homes on the propeller wash of the target ship with a reliability that acoustic countermeasures struggle to address. The Northern Fleet SSN that fires it has been shadowing the Bainbridge for 6 hours, maintaining a tracking solution at a depth where the ship's passive sonar cannot resolve it against the ambient noise of the Barents Sea winter environment. The commanding officer of the submarine has been patient. He has been waiting for a firing geometry where the torpedo's time of run is short enough that the ship has no practical opportunity to evade. He achieves that geometry at 3:39 a.m. and uses it at 3:41 a.m. The torpedo travels at 50 knots. The time of run to the Bainbridge's stern quarter is 37 seconds. The Bainbridge's sonar operator detects the incoming contact at 3:41:28 a.m., 9 seconds after the torpedo has been in the water. He classifies it, reports it, and the officer of the deck orders hard rudder and maximum speed simultaneously. The Bainbridge has 28 seconds. The ship's course change begins to move the propeller wake laterally, and the torpedo's wake-homing algorithm compensates. The Nixie countermeasure deploys and partially degrades the wake signature. Partially, the torpedo loses lock for 1.1 seconds, reacquires at a slightly different bearing geometry, and detonates at 3:42:05 a.m., not directly beneath the keel. 43 meters aft of the keel's centerline, at a depth of 12 meters, slightly left of the port propeller shaft. The 300-kilogram warhead detonates in water that is 2 degrees Celsius, generating a pressure wave that arrives at the hull in 0.027 seconds and loads the aft hull structure across the stern section with a distributed impulse force. The stern rises slightly and drops back. The port propeller shaft, which was turning at operating revolutions, receives the shockwave load at its most vulnerable point, the stern tube bearing assembly where the shaft exits the hull. The bearing housing cracks along its mounting flange. The shaft does not sever, but the crack in the bearing housing immediately begins admitting seawater into the stern tube at a rate that the stern tube packing was not designed to manage. The flooding in the aft steering compartment begins at 3:42:08 a.m. at approximately 80 gallons per minute through the cracked stern tube bearing housing. This is the first problem. The second problem announces itself at 3:42:19 a.m., 11 seconds after the detonation. The rudder control system in the aft steering compartment has gone non-responsive. The helm in the bridge registers the rudder as neutral. The rudder is neutral because the aft hydraulic actuator, which physically moves the rudder, lost its hydraulic pressure connection to the main hydraulic circuit when the shockwave fractured the hydraulic return line fitting at the actuator base. Hydraulic fluid is draining from the actuator housing into the aft steering compartment, mixing with the seawater already entering through the stern tube. The ship has no steering. In the Barents Sea at 19 knots, in a following sea with wind from the northeast. No steering means the ship begins to yaw, falling off the wind and taking the swell's beam on. Within 90 seconds of losing steering, the Bainbridge has rolled to a beam sea posture. In a winter Barents Sea, beam on is not a safe posture. The officer of the deck shifts to emergency rudder control, a backup hydraulic circuit that can power the rudder actuator from an independent supply. But the backup circuit feeds through the same return line fitting that has fractured. Emergency rudder is also gone. The next option is manual steering from the aft steering compartment, which requires a sailor to physically operate the manual hydraulic pump and steering gear by hand. In the compartment that is currently flooding through the cracked stern tube bearing housing, filling with a mixture of seawater at 2 degrees Celsius and hydraulic fluid. The third problem is not yet visible. It will become visible in approximately 12 minutes. The main heating system circulates heated glycol water through forward and aft circuits, sharing a common expansion tank and circulation pump amidships. The aft circuit serves the aft machinery spaces, aft crew berthing, and the aft steering compartment, with its supply and return lines running through a conduit chase at frame 94. The shockwave from the detonation transmitted through the hull framing and arrived at frame 94 with enough residual energy to flex the conduit chase by approximately 2 millimeters under the shock load. Enough to initiate a hairline crack at the compression fitting joining 2 sections of the heating circuit supply line. The glycol water pressure is 30 pounds per square inch. The hairline crack weeps at 3 drops per minute. In the aft steering compartment, the 2 degrees seawater entering through the stern tube is rapidly cooling the space, and the frame 94 heating circuit fitting with it. As the fitting temperature drops, the compression seal material contracts slightly and the hairline crack widens fractionally. At 3:54 a.m., 12 minutes after the detonation, the heating circuit supply line fails at frame 94. Not a rupture, but a fitting separation, producing a steady stream of 85-degree glycol water spraying into a deck covered with 2 degrees seawater. The glycol water contacts the cold surface and begins to thicken as its viscosity climbs. The aft heating circuit is now open. The glycol water is discharging into the flooding space rather than returning to the pump, and the circuit's expansion tank will empty in approximately 11 minutes. When the expansion tank empties, the circulation pump begins to cavitate. When the circulation pump cavitates, it stops moving glycol water through the aft heating loop. When the aft heating loop stops circulating, every pipe in the aft heating circuit begins to cool toward the ambient temperature of the aft hull structure, approximately -8 degrees Celsius in areas exposed to the exterior hull plating. The glycol in the heating fluid has a freeze point of -20 degrees. It will not freeze, but the domestic water pipes in the aft berthing spaces, insulated but sharing the same structural void spaces as the heating circuit piping, have a freeze point of 0 degrees. If the heating circuit loses circulation for more than 25 minutes in the current Arctic ambient conditions, the domestic water pipes in the aft berthing section will begin freezing, expanding, and cracking. When they thaw, they flood, not from one hull breach, but from 17 distributed pipe failures across 4 decks. A slow, systematic flooding harder to address than any single repair, because it has 17 sources. In DC Central, the chief engineer has been building the damage picture since 3:42 a.m. The evolving picture is worse in the specific way. Cascades are worse. Each additional problem is not additive, but multiplicative, consuming DC personnel already allocated to the initial problems. 3 simultaneous requirements. a crew sized for one. Flooding in the aft steering compartment, increasing as the bearing housing crack propagates, must be addressed at source. Manual steering must be established in that same flooding space, and the heating circuit supply line at frame 94 must be repaired before the expansion tank empties and the aft domestic water pipe network crosses its freeze threshold. All three must happen in the next 15 minutes. He has 24 DC personnel available. He stands at the DC Central Status Board for 22 seconds without speaking. It is diagnosis, not hesitation. He assigns 11 people to the aft steering compartment in 2 teams, 7 for dewatering and stern tube packing stabilization, 4 for manual steering establishment. He assigns 6 people to the heating circuit repair team. He keeps the remaining 7 as a reserve for pipe freeze prevention, pre-staging heat lamps, pipe insulation wrapping, and manual valve closures on the most vulnerable domestic water branches before the freeze window arrives. He does not go to the aft steering compartment himself. He goes to the heating circuit failure at frame 94 because the frame 94 fitting is the upstream problem. If the heating circuit is not restored, the downstream pipe freeze creates 17 new problems that a crew of 24 cannot manage regardless of how well everything else goes. Stop the cascade at its source. The aft steering compartment receives the 11-person team at 3:46 a.m. The space is in emergency red. The white lighting circuit failed when hydraulic fluid contaminated the deck-level electrical conduit at 3:44 a.m. The water is at 22 inches on the deck, rising. In 22 inches of 2-degree seawater, the damage controlman who steps through the watertight door at 3:46 a.m. encounters the specific physical reality that training cannot fully reproduce. The cold enters through the survival suit's wrist seals within the first 30 seconds, and within 2 minutes, his hands are working at perhaps 60% of their normal dexterity. The manual steering pump is a handwheel assembly on the port side of the compartment, approximately 18 inches above the current water level. He reaches it. The manual steering handwheel is a 2-person operation. 1 person on the pump, 1 person reading the rudder angle indicator and calling corrections to the helm watch via sound-powered phone. In 22 inches of water in emergency red lighting, with hydraulic fluid floating on the water surface, making every step uncertain. Establishing the 2-person team requires both people to work past each other in a space designed for maximum 2 people working comfortably. They establish the team. The first helm command comes through the sound-powered phone at 3:49 a.m., 5 degrees right rudder. The damage controlman on the pump cranks the handwheel. The rudder responds. On the bridge, the officer of the deck reports rudder response. The ship begins to come off its beam C posture. It is laborious. Each degree of rudder movement requires sustained pumping effort. And maintaining course in a following sea with manual steering requires continuous correction inputs that powered steering provides automatically. But it is working. The ship is steering. The dewatering team has located the stern tube bearing housing crack and begun the temporary repair sequence. The crack runs approximately 120 degrees around the flange circumference, at the point of maximum bending stress in a bolted flange under shockwave loading. The correct repair is a replacement of the bearing housing. The replacement part is in the spare parts locker at frame 88. But a bearing housing replacement requires a dry compartment. The compartment has 22 inches of seawater in it. The interim repair is to increase the stern tube packing compression. The packing is a gland assembly on the inboard end of the stern tube, accessible from the aft steering compartment, tightened by rotating a compression ring with a spanner wrench. Increasing the packing compression reduces the flow through the stern tube seal. It is not a permanent fix. Overcompressing the packing will cause it to overheat and fail faster than normal degradation would. But overcompressing the packing in the next 4 minutes will reduce the flooding rate from 120 gallons per minute. The rate it has increased to as the crack propagated, to approximately 35 gallons per minute. which is within the P250 pump's dewatering capacity. The chief machinist's mate reaches the packing gland at 3:51 a.m. His hands are at approximately 40% dexterity. The 2-degree water has been at mid-thigh depth during his approach, and the cold transmission through the survival suit has been progressive. The packing compression ring requires approximately 3 full turns to reach the increased compression the chief engineer specified via sound-powered phone. 1 full turn of the compression ring requires a 180-degree arc of spanner wrench movement in a space where the maximum available arc, limited by the adjacent hydraulic piping and hull framing, is approximately 120 degrees. He cannot make a full turn in one sweep. He makes partial turns, repositions the spanner, makes another partial turn. Each partial turn is perhaps 30 degrees. His right hand cramps at the second turn. He works the cramp out by pressing his fist against the hull framing for 8 seconds, then continues. 3 full turns accomplished in 4 minutes and 11 seconds. The flooding rate drops from 120 gallons per minute to 31 gallons per minute. The P250 pump starts. The water level in the aft steering compartment begins dropping. Slowly, approximately an inch per minute, but dropping. At frame 94, 6 meters forward of the aft steering compartment boundary, the chief engineer and his repair team are working the heating circuit supply line fitting. The failed compression fitting, a 3/4-inch swagged fitting on the glycol water return line, is accessible from the heating circuit service panel on the port side of the aft hull passageway. The fitting has separated at the swage ring, with the pipe pushed out of the fitting body by approximately 8 millimeters. The pipe is not broken. The fitting body is not broken. The swage ring, the ring that holds the pipe inside the fitting by compression, has fractured at one point on its circumference, allowing the pipe to push out. A fractured swage ring cannot be repaired at sea. The correct fix is a new fitting. The chief engineer's repair kit contains a bag of pipe repair fittings, and in that bag, in a small Ziploc bag within the larger bag, are 5 replacement swage fittings of various sizes. He finds the 3/4-inch size. He pulls the separated pipe end out of the failed fitting, cuts the pipe 15 centimeters back from the failure point using a pipe cutter, cutting past the deformation zone where the fracture ring compressed the pipe, and installs the new fitting using the swage tool. The swage tool is a hand-operated compression device requiring approximately 180 foot-pounds of torque to fully engage the swage ring. In normal conditions, 2 people operate it comfortably, in a narrow aft hull passageway, lying on his side to access the fitting with his arms in the service panel opening. 1 person operating the swage tool requires bracing both feet against the opposite passageway bulkhead to generate the required leverage. The chief engineer is lying on his side in the aft hull passageway, both feet against the port bulkhead, operating a swage tool with both hands extended into the service panel for 6 minutes and 40 seconds. The new fitting is installed and swaged at 4:03 a.m. He opens the heating circuit isolation valves. The glycol water pressure reads on the service panel gauge, 28 pounds per square inch. He watches the gauge for 30 seconds. The pressure holds. The aft heating circuit is restored. The expansion tank refills from the pressurized supply. The circulation pump resumes normal flow. In the aft berthing and engineering spaces, the temperature has dropped from 15 degrees to approximately 6 degrees during the 12 minutes the circuit was open. The domestic water pipes in the aft berthing void spaces have reached approximately 4 degrees. Cold, but 4 degrees above zero and 4 degrees above their freeze point. No pipes have frozen. The freeze window has been closed with approximately 8 minutes to spare. The reserve team, the 7 DC personnel held back, has spent the past 17 minutes pre-staging. Under the chief engineer's instruction passed via sound-powered phone, they have closed the manual isolation valves on the 3 most thermally exposed domestic water branches in the aft berthing spaces and installed portable electric heat lamps at the 4 locations where pipe runs pass through exterior hull void spaces. The isolation valves cut those branches off from the main domestic water supply. The crew in those berthing spaces will have no domestic water until the valves are reopened. But a pipe with no water in it cannot freeze and burst. The heat lamps maintain the ambient temperature in the void spaces above 0. It is not elegant. It is sufficient. The Bainbridge has been on manual steering for 22 minutes when the heating circuit is restored. The manual steering team, operating in water that has dropped to 11 inches with the P250 pump running, has been maintaining course in a 2 to 3 meter following sea, with hand corrections every 30 to 45 seconds. The officer of the deck on the bridge has been providing rudder angle commands via sound-powered phone in continuous call and response with the aft steering team. The ship's course has wandered between 2 degrees left and 3 degrees right of the assigned heading during the manual steering period. Not a navigation emergency, but a measure of how much work 2 people doing manual steering by hand in a flooded compartment can manage in Arctic winter conditions. The hydraulic return line fitting on the aft rudder actuator is assessed by the repair team at 4:07 a.m. The fitting body has fractured at the ferrule seat, a clean break, and the hydraulic return line is hanging free of the actuator. The line drained into the compartment over the past 25 minutes. The repair: a replacement compression fitting, a hydraulic fluid reservoir refill from the aft engineering space 2 compartments forward, and repressurization of the hydraulic steering circuit. The repair team completes it at 4:14 a.m. Powered steering is restored at 4:16 a.m. The manual steering team stands down. The damage controlman, who has been pumping rudder corrections for 30 minutes in a 2-degree flooding compartment, lets go of the hand wheel and does not reach for it again. His hands, when he removes his survival suit gloves, are pale and stiff. The medical officer examines them at 4:31 a.m. and confirms early hypothermic response in the distal digits of both hands. He is removed from watch and given warming treatment. He reports to the medical officer voluntarily. He will make a full recovery. The Bainbridge sets course for Tromsø at 4:22 a.m. The ship makes 14 knots on one operable shaft. The port shaft, whose propeller was closest to the detonation, remains offline pending bearing housing assessment, and the ship is operating on the starboard shaft only. At 14 knots, the transit to Tromsø is approximately 21 hours. One 53 to 65,000 torpedo detonated 43 meters aft of the keel centerline. One stern tube bearing housing cracked at the mounting flange, flooding rate progressing from 80 to 120 gallons per minute before packing intervention. One rudder hydraulic return line fitting fractured, powered steering offline for 34 minutes. One heating circuit supply line fitting failed at frame 94. Aft heating loop open for 12 minutes. Manual steering established by 2-person hand pump team in flooded Arctic compartment for 32 minutes. Stern tube packing overcompressed by 3 full turns to reduce flooding to P250 pump management threshold. Frame 94 heating circuit fitting replaced and circuit restored with 8 minutes remaining before domestic water pipe freeze threshold. Port isolation valves closed on 3 domestic water branches as thermal precaution. No pipe freezes. Port propeller shaft offline for transit. Speed reduced to 14 knots. Single shaft transit to Tromsø. Ship status operational. 21 hours later, making 14 knots on one shaft in a sea that had eased to 1 meter. The Bainbridge passed the Tromsø pilot station in early morning gray. The harbor pilot who came aboard noted the ice on the superstructure and the asymmetric propeller wake. He asked nothing about the aft steering compartment still running a P250 pump on a 31-gallon per minute inflow, or the domestic water isolation valves closed for the entire transit, or the heating circuit repair at frame 94, holding at 28 pounds per square inch with a field-installed swage fitting that had never been tested in Arctic sustained service. The ship entered the harbor under her own power. She requested a berth assignment. The ship could move. The ship was functional. Everything else was a matter for the yard. The yard teams who assessed the Bainbridge noted in their inspection report that the frame 94 swage fitting installed during the event was not the correct specification for the pipe size. It was one size up from nominal, installed because the correct size was not in the repair kit, and the oversized fitting was the closest available. The chief engineer had known this when he installed it. He had torqued the swage tool past the nominal engagement point, applying additional compression to seat the oversized ring against the pipe diameter. It had held for 21 hours of Arctic transit at 28 pounds per square inch. The inspection team's notation in the margin of their report in pencil reads, "Not standard, held." No further comment was added. None was needed.